All right, today we are going to begin the last section of this class in which we are going to talk about three-phase power concepts. So today will be an introduction to three-phase circuits. All right, so in pretty much every industrialized country, electrical distribution from the utility to the consumer is accomplished using a three-phase distribution system, okay? So to this point, most of the circuits that we have analyzed would be considered a single-phase circuit. And so let me be very clear about what I mean by that. So most of the circuits that we have been dealing with have a situation like so. We have a voltage source. Here I'm modeling it as a practical voltage source, and our voltage has some amplitude and some phase angle. Over here on the right hand side, we might have some load impedance ZL, and connecting our source to our load are transmission lines. So I'm splitting this guy up into discrete sections. And for the most part, we have been ignoring impedance of transmission lines. So in your home, this type of system where, say, you plug a microwave up into an outlet is described by this, where we have what we would consider a hot wire. Usually, I think a hot wire is white in most home wiring. Then we have a neutral wire. Neutral's white, hot's black. Okay, yeah, and then ground is green. All right. It's been a hot minute since I had to replace any outlets in my house, apparently. So we have our source side. Here in the middle, transmission lines. And over here, on our load side. All right. So we have a simple system like this. One thing that I'm keen to point out is that ground doesn't show up here. Okay, ground is tied usually to the neutral somewhere outside of our system. In your home, that might be literally a copper grounding rod buried in the earth to which the neutral is connected from your transformer or something like that. But we don't usually typically see a specific ground wire other than that little prong that we see on the outlets, which is tied in, right? So we don't really consider ground to be, or earth ground specifically, to be part of our system. Well, in a three-phase, three-wire system, which is very commonly used, that would look something like this. There's our A phase. Z load A, Z load B, and ZLC. A, B, B, C, capital C. Let's call this VP angle theta A, VP angle theta B, and VP angle theta C. This is our A phase transmission line, our B phase transmission line, and our C phase transmission line. And typically speaking, the A, B, and C phase transmission lines are all made out of the same size conductor of wire and are all of approximately the same length, such that they will all have approximately the same impedance, if that matters. Also notice that all of our voltages from our source have the exact same magnitude. We're going to explain why that happens, but they all have different phase angles, and we'll explain why that's happening. So before we do that though, can anybody think about why we might use a three-phase distribution system? Like why we would use what I've drawn here on the bottom versus what we have here on the top, specifically to transmit power maybe over long distances. Anybody have any thoughts? I'm not entirely sure what you mean by that. So let me approach the question from a slightly different way. I'm sorry, what was that? So all the transmission lines can really be thought of as not really a separate system because they are interconnected. But so let's think about it this way. Let's say that we have some amount of voltage VP here, right? We're delivering power to our load impedance ZL, which is exactly what our topmost system describes. How many wires does it take? 2, all right? Our bottom system, let's say we have the same voltages, similar loads, but it only takes 3 wires. So we are able to deliver 3 times as much power with only 1 and 1/2 as many times lines. It's significantly cheaper based on literally the cost of the conductors alone to deliver power over a 3-phase system. You can deliver 3 times as much power with significantly less conductors being used. So it's much cheaper in that sense. The other biggest advantage of using 3-phase power is in an induction motor. We are going to see when we get into our power analysis portion that for a balanced 3-phase system, the average power supplied by a 3-phase source is a constant value. So even though there are 3 different phases sinusoidally oscillating, the average power is constant. It has no time dependency whatsoever, no angular dependency or anything like that. So if we're able to deliver a constant amount of power to an induction motor, that means that we're able to supply a constant amount of torque, which means the motor doesn't vibrate and doesn't tear itself up. So the 2 principal reasons that we use 3-phase power are because it affords cheap distribution over long distances, and it allows 3-phase induction motors to operate with minimal vibrations, which means minimal stress on the system and therefore longevity. There is a reason that the motors in our power lab, which come from, I believe, pre-World War II in some cases, still work. And it's because of 3-phase balance systems. Right? They will effectively last forever unless you physically get in there and start screwing around with stuff, which I would highly advise you not to do when they're on. You will die. All right. So let's talk about why three-phase generation first, why it supplies the same amount of voltage per phase. This is a very, very brief description of something that you'll spend a significant amount of time on if you choose to take the electric machinery class in your senior year. And so this is just a extraordinarily abridged version. So let's say that we have a magnet. This is going to be probably a pretty crappy drawing, but I'll do my best. And our magnet is oriented kind of on a spindle. So let's say that this is our North Pole and this is our South Pole. And we are able to mechanically rotate this magnet, either in a clockwise direction or a counterclockwise direction. Well, you guys have all had Physics 202 by this point, right? So you have had Faraday's law of induction. So let's say that I put I'll try my best to draw vaguely a circle around this guy. A system like this. And I'm going to say that this is a coil of wire and it's for my A phase. This is a coil of wire. I'm going to call it A prime. Over here, I have a coil. It's for my B. This is a coil for what I'm going to call B prime. And over here, I have a coil for C. And over here, I have a coil for C prime. And I'm going to spin my magnet with some angular frequency omega in a counterclockwise direction, okay? So right now, the magnetic flux through coils A and A prime are at their maximum value in this snapshot in time, right? As that magnet rotates, let's say it rotates 120 degrees. Then the flux through coils B and B prime will be at their highest value. Spin it another 120 degrees, the flux through C and C prime will be at their highest value, and so forth, and so forth, and so forth. So if we take a moment and wire this guy up, as it were, I'm going to wire all my primes together. And I'm going to call this point that they're all wired together as my neutral. And let's jump this guy over like so. So this would be the voltage present at my C terminal. This would be the voltage present at my A terminal. Here's my neutral. Here's my B. So I'm going to define this voltage. That one's going to be a little bit harder to see. Where's my eraser? I'm going to call this guy VCN, positive polarity on the C terminal, negative polarity on the neutral terminal. This guy VBN, like so. And there would also be some voltage VAN that's a little bit hard for me to draw because of the way that I've drawn the terminals. Positive polarity would be measured on the A terminal itself. Negative polarity terminal would be measured on the neutral. So as this guy spins, what we should observe as a function of time, let's see, I'll do A in black. So it's going to start from its maximum value. Like so. I'll do the B term in blue. So it's not starting from its maximum value. Oh my goodness, I can't draw to save my life. And the C phase in red that I have these three things going on. Let me put a legend here, I guess it were. So this is V of T. Black is for A phase. Blue is for B phase. And red is for my C phase. This is my maximum value, so I'm just going to call this VP voltage. It's an RMS voltage. And so we're going to see those three guys oscillate back and forth, back and forth. It turns out that VAN is going to be, or let me do it this way actually. Look at it in the time domain first, because it'll be a little bit easier. VAN as a function of time is VPA cosine omega t. This guy's serving as our reference. The BN will be VPB cosine omega t minus 120 degrees. And VCN will be VPC cosine omega t minus 140 degrees. And there's 120 degree phase separation. So phase B is lagging phase A by 120 degrees. Phase C is lagging phase B by 120 degrees. Well, those exact 120 degree angle difference between the phases is because we are orienting our coils 120 degrees apart around what's called our stator, or the stationary windings on the outside there. Yes, sir. Yes, 240, thank you. Sorry, that's my fault. Thank you very much, yes. 240 degrees. If the number of turns in each coil is identical, then VPA, the magnitude of the A phase, VPB, the magnitude of the B phase, and VPC, the magnitude of the C phase, are all identical, and we would have only a single voltage generated. So I'm going through the effort of explaining this because I've had students say, Well, what if you have an unbalanced three-phase source? The only way to have an unbalanced three-phase source is to mechanically screw up your generator, right? So unless you literally start clipping wires and stuff like that inside it, it's always going to generate voltages that have pretty much exactly the same magnitude, and the phase angles are going to be separated by pretty much exactly 120 degrees. I say pretty much because there might be small heat fluctuations that cause the voltage to differ by a couple of millivolts or something like that, and the phase angle to differ by a couple of, let's see, it goes from degrees to seconds as a portion. So 1/3600, few 3600ths of a degree. So the variations are going to be extraordinarily small, so small that they don't do anything appreciably whatsoever. So this is a terrible drawing of a very simple three-phase generator. We're spinning a magnet, and as the magnetic flux through each phase hits its maximum, we see that our output voltage hits its maximum. So we're able to generate voltages that have the same magnitude but are exactly 120 degrees out of phase with each other. All right, so this is what's called a positive phase sequence. Specifically, when phase B lags phase A by 120 degrees and phase C lags phase B by 120 degrees, that is a positive phase sequence. If we were to spin our magnet in the opposite direction, we would have a negative phase sequence. So just to be clear here, positive, sometimes called ABC sequence, in the frequency domain, our A phase voltage is simply VP with an angle of 0 degrees. Our B phase voltage is VP with an angle of negative 120 degrees. And our C phase voltage is VP with an angle of negative 240 degrees. For a negative phase sequence, or CBA, our voltage generated, our VAN, is equal to VP angle 0. VBN is equal to VP with an angle of positive 120 degrees. And VCN is equal to VP with an angle of positive 240 degrees. Why do you think it's important that we're able to cause a positive sequence and a negative sequence in a generator? Exactly right. So if we need our motor to spin the opposite direction, we have to be able to effectively swap the wires to make it spin that way. So positive phase sequence is the motor is spinning clockwise. I can't remember right off the top of my head, so let's just call it clockwise. Negative phase sequence is it spins counterclockwise. The one spins in one direction, the other spins in the other. The speeds are exactly the same, all that kind of stuff. It's literally just changing the direction of rotation. Because it's just such a simple and arbitrary difference in this class, all of our circuits will be dealing with, will utilize a positive phase sequence because the direction of rotation really doesn't matter based on the analysis that we're doing. All right, so now we're going to get into a heavy terminology section. Okay, this is where things typically start to get confusing for some folks, all right? So the first thing that we are going to look at is what is called a Y connected source. It may be written as WYE or literally just the letter Y. All right. In many textbooks, this will be represented in the following way. I don't like, well, that'll work. We have 4 terminals, an A terminal, a B terminal, a neutral terminal, and a C terminal. The neutral terminal is technically optional. It is just the point of interconnection between the A, B, and C phases. We don't actually have to connect anything to this terminal, and we'll see why that is shortly. So I'm going to list a few voltages here. Here's a voltage VAN. So positive polarity is measured on the A terminal side, negative polarity is measured on the neutral terminal side. Here is our voltage VBN. Here is our voltage VCN. Another way, and it's my preference to represent this style of Y-connected source, is something that looks like this. A, B, C, N. Here is VAN, VBN, VCN. So they represent the exact same thing. 3 voltage sources all sharing a common point of interconnection, neutral terminal. To me, I just prefer this method. It's easier for me to see what's going on without the weird Y shapes, and we'll soon see a weird delta shape as well. So the first thing that I want to identify is what are called the phase voltages, okay? By definition, a phase voltage is simply the voltage drop over one phase of a source or a load. Okay? So for this particular configuration, our Y-connected source, our phase voltages are VAN, VBN, and VCN. Should be obvious, it's the only thing that we've identified here, but VAN, VBN, and VCN represent the voltage drop over one phase of our source, so they are our phase voltages. Okay. The next thing I would like to talk about is line voltages. Line voltages are by definition voltage drops between the transmission line terminals of a source or load. So I'm going to do these guys in a different color. So this voltage that I've drawn in green here, VAB, would be representative of a line voltage because it is measured between the transmission line terminals of the source. It's a little bit easier to do them over here. So we might have VAB, here would be VBC, and between here and here would be our line voltage VCA. That's the three principal line voltages that we'll deal with between phases A and B, or terminals A and B, between terminals B and C, and between terminals C and A. So these are our line voltages. So I'm going to write them down. VAB, VBC, and VCA. Next, we will deal with our phase currents. So a phase current is any current which flow through one phase of a source or load. And I am going to go one step further here and say specifically that it's going to be the current flowing from the positive polarity terminal to the negative polarity terminal. So our phase currents in this case would be ICN, IBN, and IAN. Like so. All right, now there are such a thing as line currents, but line currents are specifically the currents that are flowing through each phase of a transmission line. Since our source is not connected to anything, we cannot represent our line currents yet. Okay, so I want to be clear about why I am skipping over them. Now, another thing that I want to be very clear about is we're going to be using double subscript notations for literally everything in this section, okay? The first subscript for the voltage represents the positive polarity terminal. The second subscript on a voltage represents the negative polarity terminal. The first subscript on a current represents where the current is originating. The second subscript on the current represents where it's flowing. We are also using lowercase letters on the source side of things. And if you notice up here, I'm using uppercase or capital letters on the load side of things. It's because we're going to have multiple voltages that we could call VAN, one on the source side, one on the load side, and we need to be able to distinguish between them. I don't remember which of the several circuits analysis textbooks I have. One uses letters on one side and numbers on the other side, and that just confuses the ever-living bejesus out of me. So I'm going to go with lowercase letters on the source side, uppercase letters on the load side to keep things clear. All right, so this is our Y-connected source. It is a 4-terminal system or 4-terminal voltage source where, again, our neutral terminal may not actually be connected to anything. Next, let's talk about a delta connected source. I think there's enough room here. So in a delta connected source, 2 different ways to draw it. So this will be our voltage, or excuse me, our terminal A. This guy will be B. And down here, we will have C, which makes this voltage VAB, this voltage VBC, and this voltage VCA. It is a 3-terminal system. There is no neutral connection to speak of. In my opinion, more simplified way to draw this system is this guy. A, B, and C, which makes this guy VAB. And this guy B, I'm going to erase that because it looks terrible. BC. So all drawing it in this box method, all the polarities are all worked out correctly. We still have our 3 terminals. To me, it's just, again, a little bit more manageable. So using the definition of phase voltages that we defined above, what are the phase voltages for this delta connected source? This is not in any way, shape, or form meant to be a trick question. I'm just trying to reinforce what the definition of a phase voltage is versus a line voltage, etc. Because this is where the confusion arises from, and why students do typically pretty poorly in this section. So go back up to what your definition of a phase voltage is and read it aloud to me, somebody. Yeah, so it'll be, so our phase voltages will be VAB, VBC, and VCA. All right. Everybody okay with that? So we are representing the voltage drop over one phase as a voltage being supplied by each of these single phases of our source as voltage drop over the single phase of our source. What are our line voltages going to be? So if you're saying VA, VB, and VC, what are we're using a double subscript notation. What, with respect to what reference are those voltages being measured? What's the fundamental definition of a line voltage? The voltage drop seen between the two terminals where we connect to the transmission lines. So if I'm looking at the voltage between transmission line connection A and transmission line connection B, what voltage do I see? VAB. What about between B and C? VBC. And obviously between C and A, we have VCA. So for a delta connected source, the line voltages and the phase voltages represent the exact same quantity. Is that obvious? Okay. So for a Y connected source, they do not. For a delta connected source, line voltages and phase voltages are identical. Let's talk about our phase currents. So phase currents represent the current flowing from the positive polarity terminal to the negative polarity terminal over each phase of our source. So it should be fairly obvious that we're going to have some current IAB, IBC, and ICA. Where IAB is this guy, IBC is this guy, and ICA is this guy. And I can draw them here. Like so. Again, we cannot express line currents because we aren't connected to anything, so we have no transmission lines through which to measure our current. So these are our two different possible sources that we can connect to a three-phase system. There are also two different possible loads that we can connect through transmission lines to a three-phase system. So all we're going to be dealing with in this class for the next several weeks, however long till the end of the quarter is those four possible permutations of Y connected source to Y connected load, Y connected source to delta connected load, delta connected source to Y connected load, and delta connected source to delta connected load, or some variation on that, meaning that we could have loads in parallel. It's pretty much impossible to do loads in series in a three-phase system because you'd have to put each phase in series. It's just wonky as hell. And all that kind of stuff. So we might see a few circuits where it has a Y connected load and a delta connected load connected to some type of source, but it's all just boiling down to four very, very basic circuits that we'll be dealing with. So since our sources are well defined, now let's talk about our loads. Let's call this guy terminal A. This guy here, B. Here's our neutral connection. And here is C. I'm going to call that impedance ZYA, this impedance ZYB. Hold on, let me save this. Close it and reopen it because it's giving me that stupid error. This guy right here will be ZYC. And my preference is this guy. Where we have ZYA, ZYB, and ZYC. So one thing that I want to point out is that these impedances ZYA, ZYB, and ZYC need not be identical to each other, okay? So while our sources 100% of the time are going to represent a balanced source, meaning the magnitudes of all the voltages are going to be the same and the phase difference between the different phases is always going to be plus or minus 120 degrees. For our loads, that does not have to be true. We are going to start out with systems where it is true because it makes the analysis much, much easier. And then we'll work our way towards systems where those relationships are not true. And in turn, we'll have to apply kind of a different methodology here. All right. So without further ado, let's identify our phase voltages. So we're looking specifically for the voltage drop over one phase of our load in this case. So if I'm looking at this impedance ZYA, what is the phase voltage associated with that portion of the load? Yes, V capital A N. For ZYB, we would have VBN. And for ZYC, we will have VCN. My line voltages. What are they going to be? Again, line voltages are just the voltages measured between the transmission line terminals. Yeah, so V capital A, capital B, V capital B, capital C, V capital C, capital A. The exact same voltages that we saw for our source, just capital letters now. And I guess it might be useful for me to put some of these on the drawing. So let's call this guy VAN, this guy here VCN, just so we can kind of see what's what. VAB. Our currents are the ones going from the positive polarity terminal to the negative polarity terminal. So this would be IAB, sorry, not AB, AN, excuse me, ICN, IBN, BN, etc. And if we wanted to throw some on this side, IAN, BN, ICN, BAN, BBN, BCN, and BAB, BBC, etc. So, as I just pointed out, our phase currents are IAN, IBN, and ICN. All right, the last thing that we are going to have to concern ourselves with is a delta connected load. So let's throw something here. B, A, C. So let's call this guy Z delta C. This guy up here will be Z delta A. This guy here will be Z delta B. Or in the simplified box way, so these are two different ways of drawing our delta connected loads. Someone other than Mr. Burrell, tell me what our phase voltages are going to be. Mr. Mathern, what's up? So we're using a double subscript notation. So where is the positive polarity terminal and what is the negative polarity terminal of the voltage drop over Z delta A? Okay, so yeah, B capital A, capital B, etc. Yeah. V capital A, capital B, V capital B, capital C, V capital C, capital A. We got to use the double subscript notation so that we're all speaking the same language. All right, somebody else tell me what the line voltages are going to be. Exact same thing. BC, BCA. And let me write some of these guys down just real quick. Sorry, that should be negative polarity terminal on that side. our phase currents. So they're going to be whatever our phase voltages are, but we put an I and we make sure the current flows from the positive polarity terminal to the negative polarity terminal. So our phase currents are going to be this guy, no, take that back, B to C. Oh no, I drew this guy wrong, that's the issue. Sorry about that. Let me fix that. This should be positive here, BC negative there. And so our current goes this guy. So here's IBC, IAB, and ICA. And so we can see that for both delta connected sources and delta connected loads, we have the condition where the phase voltages have to be identical to the line voltages. All right, that's really all I mean, I have 13 other pages worth of notes that I brought with me, but I feel like this is actually a pretty good stopping point as far as new material. So I'm going to draw a circuit and I want you guys to help me figure out if I were asking for a specific quantity. So you know, how we could identify that in the circuit, because that's your homeworks from this point on are pretty much just going to be word problems. I'm not going to bother drawing a circuit for you. It's going to be expected that because you know what a Y connected source looks like and what a delta connected load looks like, you can kind of put 2 and 2 together and figure out what exactly the quantities are that I'm looking at. So let's say that I have the following circuit. Here's A, B, and C. My transmission lines. This is the first time that we have seen them. I'm going to call this guy ZWA, ZWB, and ZWC. They don't have to be the exact same size, meaning there's nothing, well, I guess the code tells us they need to be the same size, because if they have different impedances, then it's going to unbalance the system. But like, there's nothing physically requiring these guys to be identical. We could, if we were feeling like a real jerk, use different sizes of wires in these positions and cause things to act wonkily. Here's A, B, and C. All right, so first, should be fairly obvious. What kind of system is this? So we typically identify our systems by whatever type of source we have, and then whatever type of load we have. So in this case, we have a Y connected source and a delta connected load. So we would consider this to be a Y delta system. So source, first thing, load, second thing. So in your homework assignments, I might say you have a Y delta system. This is what I mean, okay? What are phase voltages on the source side? All with lowercase letters, right? What are our phase voltages on the load side? Everybody agree with that? That's correct. Our line voltages at the source side? Yes. Right, all with lowercase letters. Yep. And our line voltages at the load? Same as the phase voltages because it's a delta connected load. All right. So since we know what our phase voltages are, it's going to be really easy to find out what our phase currents are. It's literally just we replace the V with an I and make sure we draw the current flowing from positive polarity terminal to negative polarity terminal. So let's talk about line currents now. This is our first chance that we've ever had to look at them. And this will be the last thing that we're going to talk about today. Our line currents, by definition, are currents flowing through each phase of the transmission line. So in this case, that would be this current IAA, I lowercase b capital B, and I lowercase c capital C. So they start on the source side at that transmission line terminal and end at the load side of that same transmission line. So that's why it's lowercase a, uppercase a, lowercase b, lowercase c, uppercase c, etc. So let me ask you guys a follow-up question. What is the relationship between the line currents seen in the transmission line and the phase currents on the source side? Yeah, so they're equal in magnitude, but opposite in direction in the way we have defined our source currents. Because our source phase currents are going to be flowing from the positive polarity to the negative polarity terminal. They're in the opposite direction. Absolutely right. If we had a Y connected load, we would see that our line currents and our phase currents in the load were equal. There is technically a relationship between the line currents and the phase currents in this delta connected load, but we are not quite ready to take a peek at that just yet. It involves not a whole heck of a lot of complex math, but I want to talk about the general steps of circuit analysis before I go into weird cases like that. All right, so we have covered the majority of the terminology and all that kind of stuff for three-phase circuits. I understand that it was a pretty large amount of information for you guys to digest all in one day. So I have no issue whatsoever with you guys asking me questions about stuff, let's say on Wednesday and maybe on Friday. But after that point, if you don't know what a line voltage is or phase current, you're just pissing me off, to be entirely honest. Okay, we spent a whole day covering the terminology and trying to figure this stuff out. So within 1 week's time, you should be familiar with it enough to at least vaguely catch what I'm throwing. All right, that's my level, my expectation level for you guys, is to at least understand what I'm asking you about by this upcoming Friday. All right, that's enough out of me for today. So I'll see you guys on Wednesday, where we'll get into circuit analysis in earnest.